mean is unknown. I just rescale, right? So all I have to do is instead of n, I should do n minus 1. So that's why you should be careful about this plug-in procedure, right? We tend to do this a lot when it comes to multi-stage pipelines. We estimate some parameter, plug that in to our procedure for another estimation. So we have to be careful because the bias can, right, build up. Even though mu hat was originally unbiased because it doesn't have nice invariance properties. You know, you plug one unbiased estimation to another procedure that's unbiased. If you knew the parameter, the result is not unbiased. Right, anything can happen, right? And you make any kind of transformation of your parameter, unbiasedness is not guaranteed. Right, because only under linearity is expectation preserved, right? Under non-linearity, we don't know. So that's why it's non-trivial to get unbiased estimators. Okay, so that's an example to demonstrate that. Yeah, so, you know, if you want to like ask for this UMVU estimator, right, before we get there, let's think of a procedure to minimize the variance, right? So let's say I have g hat of y is unbiased. I start with an unbiased estimator, right? So how can I reduce its variance further? Is there any intuitive way to reduce variance further, but still keep it unbiased? So there is one, right? So if you, I guess, recall your probability, let's say Z1 and Z2 are two random variables. So if I did covariance of Z1 given Z2, is this, and then I look at the, so let me just do the scalars for simplicity. I can do the trace for the vectors. Is this lower or higher compared to variance of Z1? Just for two random variables. It's lower, right? Conditioning reduces variance. And that's intuitive, right? Because your randomness is reduced when you condition on a random variable. So how can I use this principle to lower my variance? Because I want to lower my variance, right? That's what is the goal of UMVU. I want the minimum variance. So what can I do? I have an estimator. I could condition on some function, right? I don't know what, but I can, let's say, condition on some function of y, let me call it h of y, right? So if I condition on it, I have to take, of course, the expectation, right? So this is now my new estimator. Let me call this G star. So what should be the variance of this estimator? Should be lower, right, than the original one. Is that clear? Right, so from the principle that conditioning reduces variance, we can condition on an arbitrary function of y, right? Take the conditional mean and declare it as my new estimator. And that estimator should have lower variance. Right?
Could you open that expectation condition? But I just want to see that how much it reduces. It depends on the variance for some property of F. It's not just...
Right. How much depends on the property of H? right? So I haven't come to, the age, yeah, sure. Yeah, sure. Sorry. So I haven't come to how much yet, right? So just intuitively, conditioning should reduce the variance.
That is constant, there is no difference, right?
Exactly, at least, right? So it can, so potentially by choosing a good function h, you can reduce the variance. So how should I choose h? Right, but before that, somehow this is too good to be true. Right, what are we missing? I declared this to be my new estimator. Can I compute this? Yeah, so if I want to expand this expectation, right, what would that expansion look like? Right, so what is expectation? Right, so now I have my g hat of y. What is the distribution I want to integrate this over? Right, so I have my model, right, so I can do now the, I guess, y condition on, let's say, h of y, right? What else does this depend on? Theta, right? I mean, when it's right conditional, I can do the base rule, right? So what am I missing? Can I always evaluate this estimator? What do I need to evaluate this? I wrote down the formula, right? But can I evaluate it for a given problem? What do you think? Thoughts? Yes? No? Don't worry, I want you to, share your thoughts. Yeah.
It's a problem that you don't have data.
Right, exactly, right? For this, in general, you need theta, right? That's what you don't know, right, in the first place. So that's why you have to be careful. You can't always evaluate expectations. It may seem like trivial, okay, I can write down expectations, but because the underlying parameter is unknown, I can't evaluate this expectation in general. In what case can I evaluate this?
From some distribution based on relative.
What did I just say here? Right, so when can I evaluate this? I gave the hint.
H of y is sufficient.
Exactly, right? So when it's a sufficient statistic, this conditional distribution has no dependence on theta. Right? So let me now relabel this as T of y because that's what we've been using in all the notation. Okay, so as long as I condition it on a sufficient statistic, I can keep reducing my variance, right? Or, it either reduces or stays the same, right? It can't get worse. So this is an easy procedure to reduce variance, right? But the question is, can I get to the minimum variance? Right, and there, so if you recall, we talked about different kinds of sufficient statistic. Right, so the idea is, of course, y itself is a trivial sufficient statistic, right? But you want some interesting sufficient statistics, right? Because if you condition on y, nothing happens, right? It's still the same estimator. So we'll use a notion of completeness. So in the class earlier, we did minimal sufficient statistic. That had to do with the dimension of the sufficient statistic. But now we'll use another notion which is called complete, which is to do more with coverage. So complete sufficient statistic is saying if you take expectation of this sufficient statistic, and if this is 0, it implies that it's it's only when some function of that. Yes. Yeah. So it's complete, meaning like it kind of essentially covers the domain. So let me write this down. So I'm going to take some function of my sufficient statistic and then look at its expectation. And let's say this function this expectation evaluates to 0, and this should be true. I mean, this should imply that the function is 0 everywhere, almost everywhere. Right, so what this is saying is, right, so you cannot, come up with non-zero functions for which you can turn the expectation of this to be 0. And this is true, of course, for all theta, right, because in general this is also a function of theta. Okay, so this notion of complete, it's, I guess, not as intuitive as the minimal one. But in the case of exponential family, the two are the same. Right? So for exponential family, we had the minimal one, and if you recall in terms of canonical parameters, it's also complete. So, and we'll deal with a lot with the exponential family, so that's also okay. Okay, so this is kind of a notion that if it has this property, then there's the Lehman-Schiff lemma, which says that you get the Amwu estimator if you can find such a complete sufficient statistic. Right? Important, you may not always have the existence of this complete sufficient statistic. Right? Because we've written down this requirement for a certain distribution, there may be no complete sufficient statistic. Okay, so this theorem says that if there exists this complete sufficient statistic, then you have this conditional estimator to be the Amwu estimator.
The complete one is always minimal.
Huh?
The complete one is always minimal, right? The complete.
Right. So, but the minimal need not be complete. Right, but for exponential family, they coincide. Yeah, that's a good point.
But you mentioned a minimal exists, but complete one is not necessary.
I mean, minimal, even y itself is trivially could be minimal in some case, right? So, because it's just the minimum dimension, it always exists. But completeness is this stringent property, right, of coverage. So you may or may not have this. But if you have that, then you can assure that Amwu estimator exists. And in fact, it's given by this simple conditional expectation. So you can take any simple estimator, right, that is unbiased. So you start with a very simple unbiased estimator, and if you know what the complete sufficient statistic is, you're done. Right, so that's the beauty of this procedure. It's constructive. You can start with a simple unbiased estimator and get to Amwu. Okay? But mostly this is interesting for exponential family because beyond that it's hard to find complete sufficient statistic. Okay, that's kind of the practical nature of this. Okay, so I won't do the an example, but I'll point out that in the notes I'll give an example where for this mean estimator you can just start with, let's say, the first data point, right? And then you can condition on the sufficient statistic because Gaussian is in the exponential family, the sum of the yi's is complete and sufficient. Okay, so you can condition on now taking, right, this to be your estimator, right? So let's say this is, and if you evaluate it, that turns out to be just this empirical mean estimator. Okay, so if you evaluate this expectation, you get your empirical mean. So that is the UMVO estimator. So it's not just unbiased, it's the minimum unbiased estimator. And it's intuitive, right? I mean, we always take the empirical mean, right? But for exponential family, that's UMVO. For other distributions, who knows?
Generally, can't we go and just write the definition of MSE and subject to that part and just solve it?
How do you, I mean, in closed form, how do you may not easily be able to.
That you know F, right? But you can, so you can't solve it.
It may not exist, right, in some cases. So
I just want to understand if I don't know the complete. So I just want to see that these two problems are same difficulty, understanding the complete sufficiency.
I mean, the question is how do you parameterize this constraint of unbiased stress, right? I mean, you can't kind of look at all possible estimators with this bias constraint or being unbiased. I mean, it's not any finite dimensional optimization problem, right? So we don't know how to set up that optimization problem, I guess. Okay? That's why you can't easily solve it in the general case, right? Because we don't know how to incorporate all possible estimators and impose this constraint. When you could make some finite dimensional approximation, say your estimator, if it's a linear estimator, for instance, right, then you can do it, right? If it's quadratic or something, so if you limit the complexity class of your estimator, you can do it. If you don't, then, and that's the nice thing, right? Here we are not limiting any complexity of the estimators. So if you go to learning theory, that's what we do, right? We limit the complexity of our learners. So that's more the learning theory, the generalization aspect. So that's the main difference. In all of this detection and estimation, we had no constraints on the complexity of our algorithms. And still in these simple cases, at least we can find optimal estimators and detectors. Okay, but that's a good point. So is this clear? We had, the notion of UMVO estimator, and if we can find this complete sufficient statistic, and we take the expectation of any unbiased estimator with respect to this complete sufficient statistic, we get UMVO. Okay? Any other questions?
We know that the mean square error, if you want to minimize it, really what we are doing is the minimizer is just a conditional expectation, right?
But we want it uniformly across all theta. That's what makes it hard, right? The uniformity. Otherwise, I can always get a trivial estimator. Okay, that's why this is really hard problem, right? It seems very simple when I put down the constraint. I just want to minimize my variance, right? No, you cannot. You get trivial estimators. Now I want to add unbiasedness. But how do I solve this problem? Because this is all arbitrary estimators. Okay, so it's a very roundabout way to solve this, right? It's almost, if you think of it that way, it's almost surprising that you can solve this problem. But for exponential family, we can, because there we have this notion of complete sufficient statistic. At least I don't know of any other example where completeness is guaranteed, but maybe there are some others. And that's why there is so much of development of exponential family in the detection and estimation theory, right? Because it has these nice notions of completeness of the statistic. Okay? Good. So for the next parts, I'm going to talk about, okay, so great. In many cases, we can find the AMVU estimator, right? But in many others, we cannot. So can I think about limits of how much I can bring down my variance? Right? So, if you've done information theory course, right, it's not just about the achievability, but it's also about the converse. Right? So meaning, right, I may not know how to estimate this well, but can I tell you that any estimator should have at least this much variance, right? So these are the lower bounds, right? So even if I can't compute my AMVU estimator in closed form, can I guarantee that it has to have some minimum level of variance? Right, and why this is useful is maybe it can, tell you something about the procedure, right? So you're collecting data, let's say, in different scientific applications. You can, even before computing the estimator, even in the best case scenario, you're going to get this much variance for an unbiased estimator. So with this, you can go make design choices on, should you buy more expensive instruments that have lower error and so on. Right? So having limits of estimation, right, is useful for those kind of analysis. So how do you think I can determine the limits of estimation? Or in other words, when can you expect your, so let's most limit to unbiased estimators for, the sake of this conversation. So when do you think the variance will be high and when do you think the variance will be low? Even if you could do the best thing, even if you could find AMVU, what would this depend on? I mean, intuitively, right? I'm not looking for a mathematical formula.
The data?
Right, so the data, but more importantly, what aspect of data? Right, how much is the model telling you about the underlying theta? Right? So in other words, if the data is informative about theta, right, then you can expect your error to be very low. Is that intuitive? So how can I determine that in a general model? I think it relates to your project. Right, what kind of, how do I determine if my data has a lot of information about theta or it doesn't have much information? Calculus.
Can you calculate the channel capacity?
Yeah, so we can go into, so we'll get to that, but even more intuitively, right? Before we, if you do expectations of certain quantities, you get to those kind of notions, right? But just very intuitively, right? Just basic calculus. Or if you're doing control theory, what would you think of? Right, so I mean, let's say I perturb here a little, and I look at what is the impact here. So if that perturbation is large, or if it's small, how does that tell me about my ability to estimate? Do you see where I'm going? So what do you think will be an intuitive measure?
Derivative of f or second derivative or something. The smoothness of the
Right. So some kind of curvature, right? And first of all, to begin with, I can just look at the derivative itself. So I'm going to look at the log likelihood function. So I'll use log because of convenience. So there's a lot of nice things then. Right, so what I'm going to do is I'm going to look at how this log likelihood varies with respect to theta. Right, so this is like the Lipschitz constant, right, or like stability of the system, if you think in terms of control theory. So do you think we should have this quantity to be large or we should have it to be small? What would help us estimate better?
If it was large.
Right, so you want it to be large, right? Because of course, trivially, if this is 0, what is it telling us? If this is 0 everywhere, what is it telling us? It has no dependence on theta, right? So then my error will be large, like I have no information about the underlying theta. Okay? So you don't want this to be near 0, you want it to be large, right? So that's the kind of intuition. And so what does being large here mean, right? Of course, this is a random variable, so I can't just say, let it be large, right? So I have to, again, think about the overall expectation of this and ask, maybe I can make the expectation to be large. Okay, so I can start with expectation. So what do you think is the expectation of this? Can someone do the math? Do you recall taking derivative with respect to log? What is it? Derivative of log, 1 over that, right? And if it's 1 over and I take the expectation, what do I get? So wait, did I miss something? It should not be 1. Give me a second here. Oh, sorry, no, I messed it up, right? So sometimes it's hard to do basic calculus. Okay, let's do this carefully. Because I could not, I still had the derivative. So let me take the derivative outside. Okay, then we are fine. Right, so this expectation is 1. So what is the result? 0. Right, so this is a 0 mean random variable. So the natural next thing to do is look at the variance. Right, so we'll look at the variance of this. So if it's scalar, it's just S square, otherwise it's the covariance matrix, right? So let me call this S of theta, by the way. And this is called the score function. Okay, so that's the terminology. So now I'm gonna look at the variance. Okay, or in the case of a vector, it's the covariance matrix. Okay, let me do the vector case. I'll use the notation I of theta, and this is called the Fisher information matrix. Okay, so I have this core function that's a 0 mean random variable. And now I'll take the next moment, which is its covariance matrix, which is the Fisher information matrix. So if my Fisher information matrix has a large norm, right? So let me do the scalar case. So this is
You are doing is under the correct theta,
Yes, yes. So this you cannot do it during your estimation procedure, right? So this entire set of limits is for analysis, right? So for different theta, you would have different values of this Fisher information matrix, right? But I can make my analysis in terms of how this Fisher information matrix changes based on theta. Okay, that's why I have this as dependence of theta. So this is just, in this case, the Fisher information value. Okay, so this is the scalar case. The other was the vector case where the covariance is matrix. So I'll just do the scalar case in class. You know, you can have the same thing also extend to the higher dimensions. Okay? Okay, so now in the scalar case,
So that is theta is the derivative of log, right? Not
this one.
Not the because we use expectation of S of theta. I mean that S is inside.
Oh, so, sorry, S depends both on Y. Oh yeah, sorry. Yes, you're right. So let's, yeah, okay. So if I take expectation on this, right, this, let me erase this, okay, let me make it clean. Good. Yeah, so S is both a function of theta and Y. Good point. Okay? So here there's also Y. You're right. I kind of made that implicit, but let's make it explicit. So the expectation is with respect to the model, right? You're averaging over Y here. Is this clear? So I have the score function. The expectation of the score function is 0. And then I'm looking at its second order moment or its variance, right? And that's called the Fisher information. So let's say this Fisher information is low. What do you expect your estimation error to be in that case? Even for the best estimator, best unbiased estimator. So if my Fisher information is low, how should it affect the error? Estimation. High, right? Because the variation is more. So it's and that's what this Kramer-Rao bound says, that if you have the theta hat to be unbiased, right, its variance will be always higher compared to the inverse of the Fisher information value. In the matrix case, it'll be the spectral norm, but you know, I will. I mean, in fact, you can do it in terms of covariance and the positive definite, you know, order. But we'll do the scalar case for simplicity here. Okay, so the idea is if you have this unbiased estimator, you know you cannot do better than the inverse of the Fisher information value. Okay? Right, so this is a bound. And if it is biased, but you have a bound on the bias, even then you can say, in that case, the variance is bigger than the, you know, if you recall, we had the bias square, right? Sorry, it's the derivative of that, not this directly. So I take the derivative of this and then I take its square. So again, we're just doing the scalar case for simplicity here. It's not the bias, sorry, it's only it's the actual expectation. Again, let me use some other notation here. So phi of theta is the actual expectation, whereas the bias is the difference, right? So I messed that up a little. Okay, so don't worry about the biased case. Most of the time we won't use the biased case, but you can also look at the bound on the variance also in the biased case. Okay, but this is a side note. We won't be worrying about it much. But the important one is the unbiased estimators, and here amongst all the unbiased estimators, we can get a bound on what that minimum variance should be. Is this clear? So the proof of this is surprisingly simple. I mean, it seems like, right? Like, how would you even go start proving this? But it's surprisingly simple. But any questions here before we get into the proof?
So for example, do we know something like if, for example, the cases that this achieve the lower one, or for example, when we have this complete in the previous one?
I'll come to that. I'll come to that. So let me quickly prove this, and then I'll address that question. Okay, so how many of you remember the Shor complement? Kinda? Okay, let me remind you. Right, so the Shor complement is one of block diagonalization. Right, so let's do the 2 by 2 case. Here, let's say I have a matrix A with, let's say, 4 entries. So what the block diagonalization does here, right, is multiply this matrix A, let's say with 2 other matrices. I won't write down what those matrices are, such that in the end, you get the top entry to remain the same, right? And then you have zeros in the off diagonals, and then you have like a different entry here in the bottom, and this one will call it as the Shor complement. So this is the Shor complement of the first entry. Right, so this is a linear algebra trick, and if you kind of go through the steps, this is nothing but, right, this entry minus kind of this, right, product of this with the inverse of the first entry. Sorry, they are this way. Okay, so I won't derive this, just take this as a fact. Okay, so given any matrix, I can make this into a diagonal 2 by 2 matrix. I can make this into a diagonal matrix. Okay, I can preserve the top entry, and I can get a modified entry for the bottom right, and that ends up being called the Shor complement. Okay, so this is a standard decorrelation trick. We can always use this notion of Shor complement to decorrelate 2 variables. So let's say both, right, x has 2 coordinates, and let's say this is 0 mean. And these are arbitrary, right? So x1 and x2 can have arbitrary correlation, but I want to decorrelate this. So that is, I take expectation of xx transpose, right? So I can always kind of write this. Right, so all I'm doing is expanding my correlation matrix. But now I want to decorrelate them, right? So the idea is I want to like keep my first entry to be the same, but I want to modify my second entry so that, right, this resulting covariance matrix, I mean, its covariance is same as correlation because it's zero mean, so that the resulting correlation matrix is only on the diagonal, right? So it's 0 on the off diagonal. Okay, so there's some entries here on the diagonal. So I can use the Shor complement trick, and I can decorrelate this by using this transform. So this is now, so this one will be, so I can do this, right? So I won't write this down, but the main idea is this Shor complement. Okay, so I will let me directly jump to the proof of Cramer-Rao bound, because that's what we'll use this for. Any questions on the Shor complement? Right, makes sense, right? So this is, you've probably seen this before. So the trick we'll use here is we will now define a random vector where I'll have the I'll have my score function, and then I'll have my given estimator, right? So this is any given estimator. This is a zero mean random variable, right? Because it's unbiased, this is unbiased, and expectation of score function is 0. Yeah?
Just a question. When I compute the expectation of the score, why can we split derivative and the integral?
We did, right? That's how we got it to be 0.
I mean, why can we split that? Why can I put the derivative outside the integral?
That's what we did. That's why we evaluated to 0.
Like, why?
Why? Oh, I mean, you assume some kind, of course, right, the continuity assumptions that make it possible to do that. Yes, if the likelihood does not satisfy that, you cannot.
So there is some regularity?
Yes, yes. So we assume those. Yeah.
So this lot comes in the picture generally because the people in physics thought about the exponential family, or just
right. So both. One is because exponential family, right? These results, many of them end up being for exponential family, and the other is because you have this kind of mean zero property, which is kind of nice. It also helps you with this, down the line, right? So there are many. You could have as well talked about the derivative directly, right, of the likelihood. But yeah, mostly because we look at exponential family, the log is the more natural one. Okay, so going through this, so the Shor complement, right, if I were to evaluate the Shor complement for a covariance matrix, right, so this is still, right, covariance of another variable, variance or covariance depending on if this is a matrix or a scalar. So this is still non-zero, right, in that case. So in the case when you're looking at covariance, you apply the Shor complement on a covariance matrix, the Shor complement is still positive definite. Okay, that's a property, right, because this corresponds to a covariance matrix of another transformed random variable. And so we'll use that property here, right? So if you now look at the covariance of this, right, and you're looking at the Shor complement, yeah, so what is the covariance of this variable C? Right, of course, it's the Fisher information matrix for the first one. It's the variance of your estimator for the other one. It turns out to be 1 along the off diagonal. You can evaluate it. I won't write that down here, right? That's just algebra. Okay, because again, you can switch the integral and the derivative and assume regularity. So believe me, this is the covariance matrix for this random variable. Now if I ask the Shor complement, what do I get? What is the Shor complement of I of theta? Right, I just apply this formula. Right, so it's variance of theta hat minus 1 times I inverse of theta 1. And this is positive definite. Okay, so that's how you have the Kramerov bound. It's very simple, right? It's so elegant.
That one, you mean I, right?
Yeah, so if it is a matrix, it's I. So I was, mostly thinking of the scalar case. So this is not the same as I as the Fisher information. This is identity. Right? It's just not even a line of proof. And yet it is, one of the deepest results in estimation theory. Okay, I think the construction of the score function was the crucial insight here, right? The idea that if you're looking at the Fisher information, the higher it is, the lower is the estimation error. That intuition, I think, helps. But then if you write it down as the Schur complement, right, of this, in this form, then you get the result.
So if you want that biasness, that I gonna be something depends on that.
Right, exactly. Yeah, and that's why it comes there. And then it's the derivative because we're switching the derivative integral and all that, so you get that.
So I'm just wondering, you said the Schur complement is semi-positive definite. So where do we?
Because if you apply the Schur complement on a covariance matrix, right? So this, this transformation is nothing but, right? It's transforming your random variables. So it's still a variance or covariance of another random variable, right? That's why. Does that make sense? And I hope everybody followed this proof. Yeah? Because each time I do it, I'm still in awe how simple it is. But that doesn't mean there won't be any questions, right? I don't mean in that sense. It's elegant. Let me not call it simple. It's elegant. Any questions? No?
One part is finding that covariance between those two, right? That I. Is it obvious that it is I?
Because it's the variance of S. That's the definition of I.
This is
No, right,
two.
but you can evaluate it. If you write it down, it's not that hard to see. Yeah. You can go back and check. Yeah, it's just it's calculus. Let me call it that way. Okay, so just the last result I want to quickly point out here is when is this Kramerov bound achieved, right? Meaning when is this equality? Is there any estimator for which this is equal? Of course, that estimator will be AMVU, right? Because by definition, you can't do better than that. So, but then in many cases, you may not achieve this, right? Because you may have the AMVU estimator having a strictly bigger variance than the Kramerov bound. By the way, this bound is called Kramerov bound. I don't think I mentioned that explicitly. So this is another reason, this result, why we limit to exponential family. So it turns out that the Kramerov bound is achieved only for exponential family. So it's only, right? We know it's not achieved for anything else. So when a Kramerov bound is achieved, we call it an efficient estimator, okay? That's the definition. So we call an estimator efficient if it achieves the Kramerov bound. So that's just a terminology. And we're saying that for for exponential family, we have the estimator to be efficient and vice versa. So it's only for exponential family.
That's it.
Yes, that's it.
You think about it, no, because if you think about it for the maximum likelihood, if you have billions of data, you can make sure that by large number you get something to make that thing become zero. So what I mean is that.
But you know, both play, right? On the other hand, I of theta will also grow as you have more data. Right? It's the question of can you achieve the bound, right? I mean, the actual error may be low, but can you achieve the bound is a different question. Okay, so just 1 second. There was a simple proof of this. Oh, yeah. Yeah, so for exponential family and only for exponential family, right, there exists an efficient estimator. And that estimator turns out to be the same as the maximum likelihood estimator. So maximum likelihood estimator is, right, you maximize the likelihood, right? I mean, this is very intuitive, right? I mean, similar to what we were doing in detection problem, we were looking at likelihood ratio, right? It's the same concept here. For the estimation problem, I want to ask, what is the value of theta for which my likelihood is the highest? So for exponential family, this maximum likelihood is the same as the AMVU estimator. And also it's an efficient estimator. So everything's the same. And it's not true for any other distribution, any other family of distributions. Okay, exponential family is a large class, but outside of it you don't have these nice properties. So the proof of this is surprisingly not long either. I mean, seems like very hard result, but it's not. But before I do the proof, I may not have the time today, I'll post it in the notes. It's literally 3 lines of proof, right? So I'm sure all of you can follow that. But before that, I want to use the remaining few minutes to make sure, right, address any questions. Because we went through estimation fast today, right? And on Tuesday, we'll do problem solving. Right, and I covered only some very targeted topics in estimation. It's a very big field. So the main ones we covered was mean square error, right? And it's not possible to have uniformly best mean square error estimator. But if you ask for unbiased, you can aim for that, and that's the AMVU estimator. And then we looked at the Lemon-Sheffield lemma, where we said if we have a complete sufficient statistic, we can condition any unbiased estimator and get the AMVU estimator. And then we did a deviation. We said, forget about the estimation procedure. Can I ask what is the limits of my estimation? Can I give a bound on the estimation error of my AMVU estimator, right? A lower bound. And that's what is the Kramer-Rao bound, where the idea is the variance of any unbiased estimator cannot be smaller than the Kramer-Rao bound, or the inverse of the Fisher information. Okay, and then there was a nice Schur complement proof to prove that. And then the last result, which I didn't prove, but I'll have this in the notes, is to have this nice equivalence for the exponential family. So here, you have the maximum likelihood estimator being the same as the AMVU estimator. So you maximize the likelihood, you also get uniformly the minimum variance. Okay, and then it's also efficient. So this AMVU, I guess there's some more restrictions here. This may not be always true, but the efficiency is the one I want to highlight, right? So in general, right, because you may not always have the uniformity. But that's a detail. But the main one is, I guess for this part of the proof, let me only talk about efficiency. So having efficient estimator, meaning which achieves the Kramer-Rao bound, we also get it to be the maximum likelihood for exponential family.
So for any other family, can we, this is just a question, is it possible to, for example, find some distance between that one and, for example, exponential and then, but is it possible to have something?
I mean, you may or may not, right? But what we can tell you is it cannot achieve the Kramer-Rao bound. This can't be strictly equal. If it is equal, it has to be exponential family.
But is the NLE is the best one among them, or it is not? It can be something?
Yeah, it could be something else for general distributions. Okay? Yeah, so on Tuesday in the problem solving session as well, we'll try to go over these concepts again as we look at the specific examples. So hopefully that'll give you more of a confidence in solving problems for estimation. Great, thank you.